Okay, shapes of molecules. Let's start with two bonding pairs of electrons. Good example, beryllium chloride, beryllium group 2, chlorine, form two covalent bonds. There we go, and that means we've got something that looks like that with a bond angle of 180 degrees. That's 2. Let's put that one up there. Okay, let's go 3. Beryllium boron. Good old boron. So B for boron. 1, 2, 3 electrons now. Let's have beryllium fluoride. There we go. 3 non-bonding pairs of electrons or lone pairs around each fluorine, like that. So we've got 3 pairs that are going to repel each other to be as far apart as possible, and that gives us that shape with a bond angle of 120 degrees. That is trigonal planar. That's 3. Put that there. Okay, let's do 4. So let's take the classic, which is methane. So carbon, 1, 2, 3, 4 electrons in its outer energy level. Hydrogens. Okay, and we want to draw that. We're going to show the 3-dimensional nature of it. So we've got a thick line there coming out and a dashed one going in. So we get methane and a bond angle now of 109 degrees. 4 bonding pairs of electrons. So I'll put methane up there. What should we do next? We'll do 5 bonding pairs of electrons. So this would be something like PF5. So this is where we get a bit weird, because phosphorus has got 5 bonding pairs, 5 electrons in its outer energy level, and you'd normally draw 2 paired, but we need to split those up. So we get 1, 2, 3, 4, 5, and that allows us to form 5 covalent bonds to fluorine. Okay, and that gives us this shape. There we go. And this has 2 bond angles. That's a right angle, 90 degrees, and this round here is 120 degrees. So this one has 2 bond angles to remember. Okay, let's put PF5 up in the corner over there. Let's do 6 bonding pairs of electrons. Now this is as high as we need to go at A level. So 6 bonding pairs of electrons would be something like SF6. Again, we need to do the same trick where we split the sulfur pairs of electrons apart. Get 1, 2, 3, 4, 5, 6. And then we put our F's around here. I'll put the non-bonding pairs, the lone pairs, on in a second. Apologies for the sound effects, they just make this fun. There you go. There we go. Okay, so what shape is this? This is octahedral. So we have an S, F, top and bottom, and then we have one going out there, one like that, one like that, one like that. Okay, and we have an octahedral molecule, and in an octahedral molecule everything's 90 degrees, so we only have 1 bond angle there. Okay, so we'll move that one over there. That's 6. Okay, what about the weird ones? Okay, so the weird ones, by that I mean where we've got lone pairs of electrons, non-bonding pairs. So let's pick a weird one. Let's have NH3. Okay, so nitrogen, we've got a non-bonding pair there. So that's at 5 electrons. So we pair them up with the hydrogens. Okay, so we get that. These electron pairs repel each other to be as far apart as possible. So what we've got is a tetrahedron, except we're missing one of the atoms in a tetrahedron, so it doesn't have a hat on. So it's just like that. I've got a non-bonding pair of electrons there. That's actually closer to the nitrogen than the bonding pairs are, and therefore it pushes the bonding pairs slightly closer together, and ammonia's bond angle is about 107 degrees. Okay, so that's one weird one for you. So we'll whack ammonia there. Okay, what else can we have as a weird one? Water, very important molecule if you want to be alive. Okay, hopefully you do. So oxygen, 1, 2, 3, 4, 5, 6 bonding pair electrons, 2 lone pairs we're going to have here. So we get something that looks like that. Excuse my H's. So consequently, again, we've got 4 pairs. So essentially, we have something that's based on a tetrahedron, except in this time, 2 of the atoms, or 2 of the vertices on the tetrahedron only have lone pairs. So we've got double the number of lone pairs here. So these H's get squished even closer together. So that actually goes down to about 104 degrees. Okay, so that's water. Let's whack water up there as a weird one. Let's have some ions, because ions are fun, aren't they? Oops. Let's have an ammonium ion, NH4 plus. Okay, NH4 plus, N, just like ammonia really, not much different from ammonia. So this is ammonia again, but we've got this hydrogen ion that we can stick on. So we can stick on there, and this one here, that is a dative bond. So DB stands for dative bond, okay, and that gives us a pure tetrahedron for an ammonium ion. So that's 109 degree bond angle. Okay, we'll grab water in there. Apologies, water, you've got a little bit small. Never mind. Oh yeah, that'll do. Okay, water's that tiny little thing up there, but we all know it's a bent molecule, don't we? Okay, so let's have something else. What else can we have? We can have another example of data covalent bonding, CO, carbon monoxide. So this time we have to do a triple covalent bond, which is what we've got in carbon dioxide. So we end up with something like that, where the oxygen is donating a pair of electrons to the carbon. So at the bottom is a dative covalent bond, and we've got a carbon-carbon triple bond there. So as we've only got 2 atoms, it can only be linear, of course. And let's put carbon dioxide into that little gap there. Bigger. Okay, that'll do. And we can take this and apply it to any molecule. Let's just look at a multi-centered molecule quickly. Let's look at something like this is one you'll come across in developing fuel, C2H4. Okay, this is ethene. Now ethene's got 2 carbons, and each carbon's bonded to 2 hydrogens. So if we bond the carbons to the 2 hydrogens, we get something that looks like this. Okay, and then each carbon still has 2 electrons to play around with, so we can form a double bond in the middle that looks like this. And the double bond counts as one group of bonding electrons as far as shape is concerned. So each carbon has 3 groups of electrons. So it's a bit like the BF3 up at the top around each carbon. So we end up with a planar molecule which is trigonal planar about each carbon atom with a bond angle of 120 degrees. So this is a flat molecule. All the bond angles are 120 degrees because the carbon has 3 bonding sets of electrons around it. Okay. I'll grab carbon monoxide. Let's put that over there somewhere. Okay. Let's just have one more example of an ion, because ions are fun. let's do this one quite small because I'm running out of space. I could go on to another page. Let's go on to another page. Let's be radical. Actually, let's go on to another page, isn't it? Okay, there we go. Let's see whether this works. Let's do SO4 2 minus. Now we've got a negative charge. You're adding extra electrons there. So sulfur, what sulfur got? Sulfur's in group 6. So it's like that. Okay, so what we can imagine is forming a couple of single bonds to the oxygens, like that. Now we've got a couple of negative charges, which means we've got some extra electrons to play around with. I'll just put them in a different color. So that makes those oxygens have their 8 electrons in the outer energy level. But to add the other two up, we've effectively got to imagine we're creating double bonds here and here. And what we've got is something that's got 4 sets of bonding electrons and a couple of negative charges. So what we get is a tetrahedral ion. Okay, so that should be dark and that should be hashed like that. Now the reality with this ion is that it is actually a perfect tetrahedron, and these are all partial double bonds, so there isn't actually any difference between the one going up and down and the one going into the plane. They're all equivalent. The electrons are spread over this thing equally rather than being localized like I've shown it there. So that's a quick run through bonding.